In this video, we're gonna discuss Weber's generalization of Dirichlet's theorem. Recall that Dirichlet's theorem says that if A is relatively prime to an integer m, then there are infinitely many primes B congruent to A modulo m. To understand Weber's generalization, we need to first review Dirichlet's proof. For a given character modulo m, Dirichlet has constructed the so-called Dirichlet's L function. And the key step in Dirichlet's proof is that for a non-principal character, L1 of chi is gonna be non-zero. In particular, this means that log of L1, chi is bounded. Now, the way Dirichlet used this was by establishing the following identity. On the left-hand side here, he has the Euler-Phi function together with the sum over all primes that are congruent to A modulo m of 1 over p to the s. Observe that to show that there are infinitely many primes congruent to A modulo m, it suffices to show that for some s, this left-hand side here is unbounded, because then this sum here cannot have finitely many terms. Therefore, it suffices for us to prove that the right-hand side here is unbounded for some s. Thus, it suffices for us to show that the limit as s goes to 1 of this right-hand side here is infinite. Now this term here is going to be bounded as s goes to 1 by construction. Moreover, from our previous discussion, we know that for all non-principal character chi, log of L1, chi is going to be bounded. On the other hand, the L function for the trivial character is just the Riemann zeta function, and its limit as s approaches 1 is just the harmonic series, so that sums to infinity. Therefore, this limit here has only one unbounded term, thus there cannot be any cancellation. And thus this limit here must be infinite. Thus this sum here must be an infinite sum, and therefore there must be infinitely many primes congruent to A modulo m. So that was the idea behind Dirichlet's proof of his theorem on primes in arithmetic progression. Now, imitating this proof, Weber also constructed his own L function. Instead of characters on Z mod mz star, Weber now considered characters on generalized ideal class group. Recall that we have defined this to be quotient of this group of rational ideals Im relatively prime to a given modulus m, right, over some ideal group, i.e. some group lying between Im and this p plus m. For a given number field k, a modulus m of k, and a character on some generalized ideal class group Im over h of k, Weber defines the corresponding Weber L function as follows. The definition is almost identical to the definition of Dirichlet's L function, except that now the product here is not going to be over primes, but rather prime ideals. And instead of dividing by prime, we are dividing by norm of prime ideals. In terms of summation, instead of summing over integer relatively prime to m, we are summing over ideals relatively prime to the modulus, and we're replacing these integers here in the quotient with the norm of the ideals. Note that when chi is a trivial character, then this is just the Dedekind zeta function. Similar to Dirichlet's approach, Weber also investigated the limit as s goes to 1 of his Weber L function, and using that he obtained the following generalization of Dirichlet's theorem. Weber's generalization says that if H contains all but finitely many primes of K splitting in some Galois extension L of K, then the index of this generalized ideal class group is going to be equal to the degree of L over K. In particular, there are infinitely many primes in each coset of this generalized ideal class group. Now, how is this a generalization of Dirichlet's theorem? Well, recall that we said that when K is just Q and M is just the principal ideal generated by some integer mz, then Z mod mz star can be realized as a generalized ideal class group. In that case, then Weber's theorem says that there are infinitely many primes in each coset of Z mod mz star. And that is exactly the statement of Dirichlet's theorem. Now, let's have a look at Weber's generalization again. Observe that for this theorem to be useful, we need to be able to know when its hypothesis is satisfied. Observe that for a given ideal group H of K, to use Weber's theorem to say anything about the index of H inside IM, we need to find a finite Galois extension L over K such that H is going to be equal to the set of primes of L that's split over K, with up to finitely many exceptions. Well, such a field L is called a class field for H over K, and we'll discuss that in the next episode.